Salutations, everybody. Hope you guys are doing all right. Hope you guys have eaten breakfast. If not, try to eat lunch or something like that. This is going to be a long review. Okay, so I have altered the first and every subsequent question because this is 20 points. This is 20 extra points to your exam. So I won't give you your answers directly, but these will be applicable. These will be applicable to your questions. All right, so with that said, let's go ahead and start this one. The figure below shows a horizontal rod of length 12 meters with forces acting on it. And this is the rod. What is the net torque in Newton meters on the rod about the axis through B, perpendicular to the page? Give magnitude and direction. Okay, let's start with this part right here, perpendicular to the page. What does that mean? If you've seen my earlier reviews, you'll be able to know what this is. If you haven't, no worries, I'll go over it here. Okay, so when we're dealing with rotational stuff, typically they will be rotating through, they will be spinning like so. So if V is going this way, this is spinning like this. For example, this could be like a blender, the blender blades, or maybe a ceiling fan or whatever. If V is going this way, which direction is, say, angular velocity going? Angular velocity is going in this way. I would say that it's going this way. They put it in this direction because where else are they supposed to denote the direction that it's rotating? It can't be going this way because that's where tangential velocity is. So it will be going this way. So when they say perpendicular through B, you could think of it as just this right here, except instead of this, we got this rod right here. Okay, cool. All right. So another thing I want you to note is that when omega is positive, it'll be going upwards. It'll be spinning not this way, but actually the opposite way. It'll be spinning this way. If omega is positive, if torque is positive, if angular acceleration is positive, it's whatever. It'll be going this way. And you can remember this using your right hand rule. This is your thumb. Oh dear. This is your thumb. Oh dear. This is your thumb. Right? And your fingers curled this way. Your thumb points upwards. Your thumb is pointing upwards, this is positive. The way that your fingers are curled will represent the direction that the thing is spinning. So in this case, this is your thumb. And these will be your fingers. Use your imagination, please. I'm not too good of an artist with my mouse. So since your thumb is pointing upwards, it's going to be positive. If this rod is spinning this way, it'll be spinning in the positive direction. The torque will be going the positive direction. Any other direction, if it's going the opposite direction, it's going to be negative. So that's a recap over the right-hand rule. Really quickly, what is the net torque in Newton meters on the rod? Okay, so go ahead and recall the formula for torque. Okay, the formula for torque is going to be, well, this funky looking T, that's torque. It's going to be force perpendicular to the distance that the force is being applied. So if we have this rod and I apply the force like this, and the rod rotates through this point. Let's say our axis of rotation is going to be here. Our force that's going to be applied is going to be our torque that's going to be applied is going to be equal to force times distance. Now, if the force is at an angle, such as this one right here or this one over here, then we have something different going on. I'll say this is half d. If we have this angle right here, we're going to need the part of the force that is perpendicular to the distance, which is going to be this part. Not this part, because this part is not perpendicular. Perpendicular Always looks like this. You're going to have a 90-degree angle between either two vectors if it's perpendicular. So you need this side. Using this angle, you would see that it's going to be f times sine of theta. It isn't always going to be sine of theta, but in this case, it's going to be f sine of theta times d. So with that said, let's go ahead and calculate the net torque on this rod. Okay, so going through B, B is our axis of rotation. So let's start with, I guess, let's use this force. Let's start with that one. Net torque, which is denoted this funky looking T, sub 0 is going to be equal to this force, which is going to be 150 newtons, and it looks perpendicular to the distance, so we don't need to multiply it by anything else, and then times the distance that is being applied. So if the entire thing is 12, and this is divisible by 4, then this part right here is going to be 3. It's going to be 3 meters. How did I get that? Well, 1, 2, 3, 4. 12 divided by 4, that's 3, and this part is 1/4. So that's going to be 3 meters. So that's the torque from the 150 Newton force plus, let's go for this 400 Newton force next. 400 Newtons, and let's see if this is positive or negative. Well, the perpendicular part is going to go this way, so it's going to cause it to spin this way. And if we're using our right hand rule, we can see that it's going the opposite way of our fingers, so it's going to be negative. It's going to be minus 400 newtons times, well, if this side right here is our perpendicular side, we're going to be using cosine of this angle. See, I told you, you're not always going to use sine. In this case, we're using cosine. They're going to get you like this if you're not careful. Don't let them get you. You want to get them. Yeah. Don't get got. Got to get got. Whatever. Okay, so if we got this right here, we'll move on to this over here. Oh, we need to multiply it by the distance. Correct. So the distance between here and D and B, my bad, is going to be half of this 12-meter rod, which is going to be 6 meters. So this is going to be the torque applied by the 400 Newton force. And then now the 350 Newton force, let's go ahead and calculate that one. The perpendicular side is going to be like this. And this is going to be positive. Plus 350 newtons times. And from this angle, the adjacent side is going to be, the perpendicular side to the distance is going to be the opposite side. So we're going to use sine of 30 degrees times the distance from B, which is going to be 6 meters. And this is going to be your net torque when you do all these calculations. What about B? What force should be placed at point D, perpendicular to the rod, to prevent the rod from rotating? Give magnitude and direction. So if we're applying a torque at D to avoid this from spinning, we're going to need to calculate this. Okay, so I'll be back after I calculate this. All right, so after calculating, we get a net torque of negative 675.14 Newton meters. So if this is our net torque, which way is the rod going to spin? The rod is going to spin in the clockwise direction because this is the negative direction. It's going to move like that. So as you can imagine, if it's spinning like this, where would you need to apply a torque? What direction would the torque need to go? Would the applied torque need to go to prevent this from moving? The answer is pretty simple. It's going to be going this way, the opposite direction. Okay, so if we're doing that, we're going to need a torque that is going to be opposite. It's going to be opposite of this, which is 675.14 Newton meters. We're going to need a torque like this. So if it's being placed at D, our distance, right, since torque is equal to force perpendicular times some distance, our distance in this case is going to be 6 meters. So if we set this equal to 675.14 Newton meters is equal to force perpendicular times 6 meters. To find force perpendicular, we just divide this by 6. And we get that force perpendicular is equal to 112.523 repeating newtons. So in other words, if we apply a force in the positive direction, like this, of 112.523 repeating newtons, we will prevent this rod from spinning. All right, question number 2 asks, a 5.54 kilogram cylinder rolls without slipping on a rough surface at an instant when its center of gravity has a speed of 11.4 meters per second. Determine the following: a translational kinetic energy of its center, and we'll stop there. We'll just go ahead and address this part. So, we call the formula for kinetic energy translational kinetic energy. The formula for translational kinetic energy, which I'll denote as KE, is equal to 1/2 mv squared. mv squared, where m is the mass and v is the velocity of the object. Okay, so from here we have the mass, we have the velocity, so we can find this. It's going to be 1/2 5.54 kilograms times 11.4 meters per second squared, and this is going to be equal to 359.9892 joules. Part B asks the rotational kinetic energy about its center of gravity. Okay, so we'll call the formula for rotational kinetic energy. The formula for rotational energy, which I'll denote as RE, is equal to 1/2 I omega squared. So we're missing two things apparently, which is going to be I and omega. They give us information that we are dealing with a cylinder. So in this case, the cylinder has a moment of inertia. The moment of inertia for a cylinder is going to be 1/2 mr squared, given that this is a solid cylinder. If it's a hollow cylinder, then it's mr squared. But we're just going to be dealing with this for right now. So let's go ahead and put that in there. 1/2 mr squared. But we're still dealing with an unknown, which is going to be omega in this case. So to take care of omega, what should we do? If you're stuck at this point, that's okay. How you solve for this is going to be you find a formula for omega, which in this case is going to be its how to convert linear velocity into angular velocity, which is going to be omega times r is equal to velocity. But we're trying to replace omega, so let's go ahead and isolate omega over here. So omega is equal to v over r. So now when we put that in place of omega, we get the following. I'm just going to reduce this in 1/4 mr squared times velocity squared over r squared. And as you can see here, r squared cancels each other out, and we're just left with 1/4 mv squared. So from here, we are given the mass and the velocity of the object, and we're able to calculate the rotational energy using this. So in this case, it's going to be 1/2, well, actually 1/4, 5.54 kilograms times 11.4 meters per second squared, and this is going to be equal to 179.9946 joules. And lastly, its total energy, its total kinetic energy is just going to be the sum of these two, which is going to be which is going to be 539.9838 joules. Question number 3 states, using a ruler and a protractor, draw a vector of 12 meters per second oriented at 200 degrees. Use a scale of 1 centimeter equals 3 meters per second. Angles are measured counterclockwise from the positive x-axis. Clearly draw the components and measure them. Okay, so for this, I am working digitally, so I do not have neither a ruler or a protractor except for that one over there. But I'm working with MS Paint, so it's not going to go too well. So I'm going to be using a little bit of estimation here. So let's go ahead and see if we can measure the 200 degrees. Alright, so from right here, you can see absolutely nothing. But if we can act like we can see, right about here is 180. So if from here to here is 180, that means 200 degrees is somewhere in this region over here. So if I rotate this 180, put this down here, I can see that I just need 20 degrees plus on top of the 180 to get 200. So you can see that interesting. Okay, and we can see that the angle is going to be going through right here. Let me go ahead and paste this in a different layer. Okay, right there. Cool. Okay, so the angle is going to be going through right about there. Okay, and with that drawn, it says 1 centimeter equals 3 meters per second, but I do not have a ruler, so I'm just going to estimate like this. Now it says the x component and the y component from here, and what you would do here is just measure. If you're looking for the x component, which side would you measure? You would measure the x side, which is going to be over here. So you'll measure from here to here, and you'll use this conversion to convert your centimeters into meters per second. And then for the y side, you would measure this and do the same thing. And you'll be able to acquire this and this. Lastly, show how you add this vector to another vector of 20 meters per second, magnitude of 20 meters per second of magnitude, oriented at 45 degrees. Use both the head to tail and theoretical method, and compare the results of these two methods. Okay, some of you may be asking, what's the theoretical method? Because I certainly am. So I had to go look it up really quickly, and I found that the theoretical method is simply the method where you use math to use trigonometry and math to calculate the resulting vector. So in other words, vector 1x plus vector 2x equals resulting vector x, and vector 1y plus vector 2y equals resulting vector y. And lastly, resulting vector, the magnitude, is going to be equal to the square root of rx squared plus ry squared. As far as the head to tail method, what this is going to entail is, no pun intended, we're going to be adding to this vector a 45 degree vector and has a magnitude of 20 meters per second. Of course, you'll be using this scale right here to go ahead and add it. Could end up somewhere over here probably. And then afterwards, you would just measure the resulting vector. The sum will just be from the center. I'm going to draw this in green, from the center to this point right here. And you would need to calculate the components of this new vector. So the components are going to be x and y. And that's question 3. Okay, this is number 4. I'm not going to read. Just going to get straight into it. Okay, so when does the person have his or her greatest speed? How much is that speed? Explain. Okay, so before we answer this question, we must look at this graph. What are we dealing with? We're dealing with position versus time. Okay, so what does that mean? What does that mean? It means 2 things. 1, slope is equal to position over time. Which is equal to meters per second, which is equal to velocity. Area, the area of the graph is equal to nothing useful. This area right here, not exactly sure what it means, but this is the same as multiplying position times time. What does that mean? I'm not sure. How long you were in a specific position? Sure, you can do that if you want to, but the area in this case would be nothing useful. Before I go ahead and solve this, let me go ahead and do a what if. Let's say that this is, instead of it being position versus time, let's say that it is speed versus time, or yes, speed versus time. Let's do speed versus time. Okay, so what would the slope be? The slope would be speed over time, which in this case is going to be equal to meters per second over seconds, which is equal to meters per second squared, which is going to be acceleration. That's going to be the slope in this case, if it were speed versus time. As for area, speed times time will give you displacement. Or actually, in this case, it's not displacement, it's going to be distance. No, I'm right. It's going to be displacement. Okay, that's cool. All right, so now that we know these 2 things, let's read question number 1A again. When does the person have his or her greatest speed? How much is that speed? Okay, so let's look here. If we're dealing with speed and we know that the slope is speed, let's see, where is this slope the greatest? Well, slope is going to be x over y, right? So the greater y is, the greater this slope is going to be. So what we're looking for is for something that is less flat and more vertical. So let's see here. We could say here looks pretty peak. It's definitely sharper than this right here. So could we say from 0 to 2? Well, that would be correct if this was asking for greatest velocity. Notice that this is upwards. This is positive, right? This, among the positive slopes, is going to be the greatest. This right here would be negative, so it would be less than the. It would have a lesser velocity than this one. However, we're not talking about velocity. We're talking about speed. Remember that speed is equal to the magnitude of velocity. This is a scalar quantity, meaning it has no direction. Okay, so with that said, we're dealing with speed. We're looking for the greatest magnitude of velocity. Well, this is not supposed to be that. This is just supposed to be position. Oh dear. Okay. Well, if we're looking for greatest speed, all we would need to look for is please ignore what I'm doing on this side. Oh dear. Wow, it's fruitless. Okay. So if we're looking for the greatest speed, we're just looking for the greatest magnitude, which in this case, let's go ahead and calculate the slopes here. This, from here to here, this slope is going to be so this is going to be 20, which is, so we're going to be dealing, okay, so for example, if we're dealing with this, and this is our x, and this is our y, our slope is going to be equal to y divided by x. Change in y per change in x. So in other words, the greatest change in position, ignore this speed part, the greatest change in position over a change in time. The higher this change in position is, the higher the slope is. And since the slope is velocity, the higher the speed is. Well, the higher the velocity is as well. But let's go ahead and calculate. So, time here is 2. And time from here to here, position from here to here, the difference is going to be 20. So the slope in this case right here, is going to be slope in this case is going to be just 10 meters per second. Go ahead and expand this so we write this better. So that's 10 meters per second right there. Okay, so what about from here to here? Well, we're dealing with a change of 4 seconds. 6 minus 2 is 4 seconds. And from here to here, we're dealing with a change of 15. Yeah, 15. So 15 divided by 4. It's going to be 3.6 repeating, I believe. So 3.6 repeating meters per second. From here to here. And the reason I'm going in such specific chunks is, well, when this line bends, the slope changes. So I'm just going to where the slope is constant. So from here to here, the difference in time is going to be 4 seconds. And the change in distance is going to be 45. So we're dealing with 11.3 repeating meters per second. Right, 45 divided by 4, 11.3. Yeah. This is going to be 11.3 meters per second repeating. So what about from here to here? Well, We could calculate these last parts, but just take my word for it and understand that these two are going to be less than any of these that we calculated so far. So, oh, this is negative, by the way. Okay, so actually, let me just go ahead and calculate the rest. 10-second difference from here to here, 15, 20. It's going to be 2 meters per second. And then from here to here, 15-meter difference, 4-second difference. It's going to be negative 3.6 repeating. Okay. So the greatest speed, remember speed is going to be the greatest, is going to be the magnitude of velocity. So it doesn't matter that this is negative. We're just going to take the number part, which is 11.3. This is just going to be, this part right here is going to be just 3.6 repeating. So if we're going based off of that, we can see that 11.3 is going to be the greatest speed here. So that's between 6 and 10. 6, which is less than t, which is less than 10. And this is going to be 11.3 repeating meters per second. B asks, what is the person's displacement from 6 seconds to 20 seconds? So let's see. At 6 seconds, we are in this position right here. At 20 seconds, we're right here. So the difference between here and here, 5, 10, 15, 20, 25. Well, actually, let me not do that. Let me go ahead and establish something first. Remember that displacement symbolized by this symbol is going to be equal to the difference between the final position and the initial position. So for example, if we were here, right? If we were here and we walked from here to here and from here to here, our displacement would just be from here to here, because this is our final position and this is our initial position. This is different from distance, which is something we will cover later. Okay, so if we're just dealing with final position and initial position, the final position is 20 meters. And the initial position is 45 meters. The displacement then is going to be negative 25 meters. What is the person's average velocity from 20 seconds to 24 seconds? 20 seconds to 24 seconds. Okay. So now we are dealing with from here to here. 20 seconds to 24 seconds. Let's go ahead and recall the formula for average velocity. Velocity average is going to be equal to change in displacement. It's going to be equal to displacement over change in time. So the change in time is going to be equal to 4 seconds. And the displacement is going to be equal to 15 meters. So its average velocity we've actually calculated already here, but this is how I calculated it before as well. So that's going to be our average velocity. Explain how you calculate average velocity when a graph is given and then plug in the numbers. Well, I just explained it to you, and that explanation is quite possibly the best explanation anybody has given anybody ever. Of course, I'm being sarcastic, but I think you got that. Let's see. What is the person's average speed from 20 seconds to 24 seconds? We just did that? No. What is the person's average speed? Okay. Okay, cool. So the average speed is going to be different from average velocity only that um, average speed is calculated using distance rather than displacement. So speed average is going to be equal to d over change in t. So back to this example over here. The distance between here and here, which I'll note in green, this is going to be change in d. The distance between here, the distance that we take from here to here, however, this is going to be d, the distance that we travel. So, for example, if you borrow your friend's car and you drive, say you drive downtown and then you're very close near to home, and they call you and they ask, where are you? You're going to say you're this far away from home. Now, if you're not paying for gas, perhaps how far you drove the car is going to be important. So they're going to ask you, what distance did you cover? This is the distance you covered. And that is the difference between displacement and distance in that case. Alrighty. If that analogy helped you, subscribe. And if you already subscribed, unsubscribe. I don't know. Okay, let's see. So the average speed is just going to be, in this case, the distance that's traveled. The distance traveled is going to be 15 meters. It's going to be the absolute value of the displacement in this case. So it's 3.66 meters per second. Just going to be the positive of what we got for D. That is the difference. Okay. E asks, what is the person's acceleration from 0 to 2 seconds? And explain. Okay, so from 0 to 2, let's see. 0 to 2. Let's go ahead and define acceleration first. Acceleration. A is denoted with the symbol A, which is going to be equal to change in velocity over time. So now that we know that we're dealing with change in velocity, let's look for change in velocity. Okay, so from 0 to 2 seconds, is there a change in velocity? The answer is no. The slope is constant between 0 and 2 seconds. It's like you driving constantly at 30 miles an hour for, 10 minutes. There is no acceleration there. So in this case, the acceleration between 0 and 2 is going to be 0. 0 meters per second squared. The reason why? The velocity doesn't change. What was the person's total distance? Explain how you find total distance. Then plug in the numbers. Okay. So the total distance is going to be very similar to total displacement, except the signs do not matter. So for displacement, what we would do is the difference between here and here, we would add, so this is positive 20. Let me denote this in purple perhaps. This is positive 20. From here to here, this is going to be positive 15. From here to here, this is going to be negative 45. From here to here, you're going to have positive 20. And from here to here, you're going to have negative 15. Now, total displacement, you add all these up and you'll get a total displacement of about, negative 5. So 20 plus 15, that's 35, minus 45, that's negative 10, plus 20, that's going to be positive 10, minus 15, that's negative 5. But if we're dealing with total distance, we do not care about the signs. We're just adding the number values. So in this case, distance is going to be equal to 20 plus 15 plus 45 plus 20 plus 15, which is going to be, give me a second, this is a lot more numbers. This number is a lot bigger than the number of fingers I have on my hands, so it's going to take me a second. 40 85, 90, 100. Take the square root. Raise it to about 54. And we get 115. We get 115. I'm not sure if that's correct actually. 20 plus 15 plus 45 plus 20 plus 15. Yeah, that was correct. Okay, so we get 115 meters. That's how you calculate total distance. How many times was it at the 15 meter mark? And at what times? Show on your graph. Okay, 15 meter mark. So what does this mean? It just means this graph keeps track of the person's position. So we want to know when this person was at a position of 15. How many times this person was at a position of 15? So let's see. At 15, we have one here. We have another here. We have one more here. We have one more here. So, as far as I can see, there are 4 times where this person or thing is at the 15 meter mark. And at what times? Okay, so it's at four times was it at the 15 meter mark. And the times is going to be, well, if we estimate here, this might be a little less than 1. So let's do 0.8. 0.8. This one right here is just going to be a little less than 9, so probably 8.8. So right here is close to 18, 17.8. And this right here is close to 21, so I'm going to use 21.2, maybe 4. Yeah, no, 2. 2 is fine. When is the person speeding up in the negative direction? Okay. So to speed up in the negative direction, that's a bit of a mouthful, but that essentially means decelerating, speeding up in the negative direction. That's the same as saying, okay, hold on. I guess you could say this is very similar to say jumping in the negative direction. You're going into the ground. You could have said you're going into the ground, but they're the same thing. So speeding up in the negative direction. Let's see. I guess you could say, let's look at these velocities. So we went from 10 meters per second to 3.66 meters per second, and then we went to negative 11.3 meters per second. So I would say right about here, this right here, there's a decrease in speed. Right about here, there's a decrease in speed. Here, there's an increase in speed. And then right here, there's a decrease in speed. I did say earlier that there is no acceleration, but that's along this line. As soon as it crosses right about here, the speed changes, and there is an instantaneous acceleration. So I would give it about maybe 2 seconds, 6 seconds, 10 seconds, and 20 seconds. When was the person moving away from the motion sensor? Okay, so assuming that this motion sensor is working the way I'm predicting, which is that we have a motion sensor here, and this person is here, the distance that it's outputting is going to be this distance right here. If it works this way, then if we're looking for when they're moving away from the sensor, so when they're moving this way, then the distance is increasing. The position is increasing. So it's going to be moving away from the sensor anytime that their position is increasing. And their position is increasing whenever their velocity is positive. So here, 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 and that's about it. So t is equal to from 0 to 2. Well, from 0 to 6. And then from 10 to 20. Okay, now we're dealing with question 5. The figure below shows a block of mass m equals, you know what? Boom, change the question. Okay, the figure shows a block with mass m equals 7 kilograms pulled up a rough surface inclined at an angle of 40 degrees with a force of magnitude F equals 50 newtons parallel to the surface. Right here, they want us to write a free body diagram. Draw a free body diagram for the system. So let's go ahead and do that. Before I do, you go ahead and try it. All right, you ready? Okay, here we go. All right, so first force I could think of is going to be gravity. Gravity is important. It keeps us down to earth, at least some of us. Not me, though. I just decide to stay on earth. Okay, so in the other direction, we have normal force. And you might be wondering, why is it not opposite of gravity? Why is gravity going straight down? Gravity always pulls straight down. Doesn't matter what your orientation is towards the earth. You could be lying down, you could be doing a cartwheel, it'll always pull you straight down. Normal force, however, depends on the surface that the object is in contact with. It is a contact force in this case. The ramp pushes against the block, preventing it from going into the ramp. Okay, so let's see. We also have force, pulling it this way. And lastly, we have friction. We have friction. How do we know we have friction? It's because they say right here on a rough surface, Whenever they say that, they probably want you to use friction. It's not necessarily they want you to, imagine the feel of the ramp. Perhaps if that helps you remember that there's friction. Yeah, sure. They just want to tell you there's friction though. And that is basically all the forces. Oh, one more. We also have the force of attraction to me. I'm joking. Okay, so let's see. B, calculate the static friction coefficient that prevents the system from moving. Okay. Go ahead and make an attempt at B. All right, ready? Okay, here we go. I am here to save you. So I'm going to go ahead and redraw this system, only because it helps me visualize it a little better when I can redraw it. So we have force normal, which I'll draw in this direction. Force of gravity, which goes straight down. And of course, we want to break up the forces into components that match the axes. It's always easier to deal with components when you can break them up into one of two axes. So we'll treat this as one axis, this as one axis, and this as another axis. This is another axis. This will allow us to use our kinematic equations, or our we will allow us to use our equations, because our equations deal with one-dimensional forces. One-dimensional, Okay, so this is force of gravity, and this is our angle right here. How did I know my angle was right there? Ooh, that's a long talk, buddy. I'm gonna be honest. See if you can find a video on this. on incline ramps. Okay, so see, this side is going to be FG cosine of theta, and this side is going to be FG sine of theta. FG stands for force of gravity. It's just, it's my way of writing it down. In this way we have force, and in this way we have force of friction. Okay, cool. Now we can write down our equations. So opposing force normal, assuming that it's not moving, we can say that they're equal. Force normal is going to be equal to force of gravity times cosine of theta. It's not equal to force of gravity because they're not opposing each other. This one's coming in at an angle. But if we can see that they're opposing each other, which force of gravity cosine and force normal do, we can say that they're equal to each other. If it's not moving in these directions, we can say that these are equal to each other as well. Oh, but don't forget this one down here, because it's also adding to it. So force of friction plus Fg sine of theta is going to be equal to F, assuming that this block is not moving. We know that this block is not moving because the system is in equilibrium. Equilibrium is a fancy way of saying ain't nothing happening. Okay. So static friction coefficient. What is that? Remember recall the static friction coefficient. It's going to be this lovely symbol right here. They call this mu. And I promise this mu has nothing to do with this mu. It has nothing to do with this mu. This is a Greek alphabet. And this just symbolizes, to at least in friction, typically symbolizes the coefficient of static or kinetic friction. In our case, it's going to be static friction. And as far as I know, most of you remember it's like this. Force of static friction times force normal is equal to, coefficient of static friction times force normal is equal to force of static friction. Okay. So, okay. So we can solve for this if we know these two. We can solve for this. So do we know this? Well, I think we do. We have it right here. What about this part? Well, we almost have it. We have it present in this system. We just need to isolate it. So let's go ahead and isolate it. There we go. Okay, so now we have these two present in our equation. We can go ahead and substitute them in. Force of static friction is equal to that, and force normal is equal to this. Multiplied by coefficient of static friction. Now we just divide both sides by Fg cosine of theta, and we achieve our final answer. Our final answer will be equal to F minus Fg times sine of theta. All this divided by Fg cosine of theta. Okay, on to part C. Instead of having static friction, there is no friction between the block and the surface, and the block moves. What is the magnitude of the block's acceleration? Okay. So what this is asking is, imagine all the grip. Imagine imagine for a second you're pushing against the door, right? You're pushing against the door. You're pushing against the door because all-time sexy man, me, is on the other side. And if I get in, terrible things will start happening. I will push open the door and I'll look at you and I'll start mewing. But in all seriousness, let's say you're preventing somebody from coming inside, right? And then the floor slips, and then all the friction in the floor turns off. How? I don't know. And then what will happen? You will slip. And you'll possibly go this way. And that's all they're asking here. Imagine this right here. All the friction turns off. All the rough spots in the ramp all disappears. It becomes ideal. It becomes a perfect ramp. What happens? What would the acceleration of the block be? All right, let's see. Let's go ahead and draw this diagram one last time. Okay, now we have new equations. Our equations are going to be Fn is equal to Fg cosine of theta and let's see, f of x, the force in the x direction, is going to be equal to F minus Fg sine of theta. So this doesn't contribute to our acceleration whatsoever because this keeps us planted, not phasing into the ramp, so to speak. This right here is where we're curious. So how do we acquire the acceleration of the block from here? Well, it will require you to recall the formula for force. Force is equal to mass times acceleration, right? So take the mass of the block and divide the force. So divide both sides. And what we'll get is force divided by acceleration. Oh, wrong. That's wrong. That's very wrong. Force divided by mass is equal to acceleration. It's that easy. So force minus force of gravity sine of theta. This is a force. All of this divided by mass is going to be equal to the acceleration you so desire. And that's question 5. This is the question number 6. As you can see, there's a 6 here. So a swimmer bounces straight up from a diving board and falls feet first into a pool. She starts with a velocity of 3 meters per second. You know what? Nah. She starts with a velocity of 12 meters per second and her takeoff point is 4 meters above the pool. How long in seconds are her feet in the air? Okay, so you might be asking, why are they asking for her feet in particular? Are they weird? Perhaps, but that is not the conclusion I will come to. The conclusion I'll come to is because they are the first thing that will come into contact with the pool because she goes feet first. We do not have to consider her height. We're not asking for anything else. So the lowest point of her body, which is going to be her feet, is going to be the easiest, is going to allow us to easily calculate what's going on. So how long in seconds are her feet in the air? Let's see. What will we use to solve this problem? Go ahead and take your time. Think. Use that noggin. Okay. We're going to be using our kinematic equations. See if you can recall them, because that's what we're going to be using here. All right, time's up. Velocity final squared is equal to velocity initial squared plus 2 times acceleration times displacement. Velocity final is equal to velocity initial plus acceleration times time. And lastly, distance final is equal to distance initial plus plus velocity initial times time plus 1/2 acceleration times time squared. Ooh, okay, so how long are her feet in the air? Let's see what we have. Let's see what information we have. We have our initial velocity, which is equal to 12 meters per second. We have our takeoff point, DI, which is going to be 4 meters. And we can deduct? We can deduct the final position. The final position is going to be when the toes come in contact with the water. The water at a height of 0 meters per second. Our velocity final is unknown, but our acceleration is known. Our acceleration is going to be negative 9.8 meters per second squared. Where did I pull this out from? This is gravity. And because we're only dealing with vertical stuff, we can assume that we're going to use this acceleration, use gravity in place of acceleration. Okay, so let's see. Let's go ahead and underline what we know. What we have. We have velocity initial, we have acceleration, we do not have, well, we do have change in distance. We do have change in distance. The change in distance is going to be d final minus d initial, which in this case is going to be negative 4 meters. So we do have it. We do not have velocity final. We have velocity initial. We have velocity initial. We have acceleration. We do not have time. Yeah. We have distance initial. We have velocity initial. We have acceleration. We do not have time, but we do have distance final. So we can use any of these equations to acquire some information, which we will then probably use to acquire more information. Okay, so what I would go for here is this one up here. You could go for this one and say you only have one variable to solve for, but this is a quadratic equation. You would have to use the quadratic formula to solve for this equation. So I'll go ahead and use this one up here, find this final velocity, plug it in here, and find this time. So let's go ahead. This velocity initial is going to be 12 meters per second squared plus 2 times negative 9.8 meters per second squared times the displacement, which is going to be negative 4, is equal to velocity final squared. This is all going to be equal to 222.4, which the square root of to acquire velocity final is going to be equal to 14.913 meters per second. Okay, now we've acquired our final velocity, we can go ahead and acquire our time. So 14.913, and hold on for a second before we go any further. Velocity final is not going to be positive, it will be negative, because this person, by the time they're heading downwards, the velocity is going to be negative. Now you might be asking, why couldn't we acquire a negative velocity from here? It's because you can't square root a number and get a negative number. That's not how these numbers work. At least if we're dealing with real numbers. You can't square root a negative number because you'll get imaginary numbers. So we couldn't acquire a negative number. But using our imagination, we can see that on the way down, the velocity is going to be negative. So negative 14.913 is equal to the initial velocity, which is 12 meters per second, plus plus acceleration, which is negative 9.8 meters per second squared, times t, which is unknown. If we go ahead and solve for t, what we'll get is 2.746 seconds. So the amount of time that this person spends above the water before the dogs enter the water is going to be 2.746 seconds. Part B asks, what is our highest point in meters above the board? Let's see, how do we solve this? Go ahead and take some time and think of a solution, and then come back when you're ready. Okay, the solution is deduced as so. Deducted, whatever. So, if, for example, we throw a ball, right? It has an initial velocity upwards because we are throwing the ball. We throw the ball upwards. It will eventually reach a maximum height to where it will fall down from. At its maximum height, its velocity is going to be 0 meters per second. So we'll go ahead and use this logic to deduce the highest point above the board that this lady acquired. Let's write down the information that we have. Our initial, which is going to be 4 meters. That's our initial position. Our initial velocity is going to be equal to 12 meters per second. Our final velocity, deduced by this, is going to be equal to 0 meters per second. The time is unknown. The change in distance is unknown. So let's go ahead and see what equations we're going to use. Okay, as always, I will underline what values I have. We have velocity final, initial, acceleration. Oh, I forgot to write down that we have acceleration. Acceleration is equal to negative 9.8 meters per second squared. Okay, cool. So we have acceleration, we do not have distance. We have final velocity, we have initial velocity, we have acceleration, we do not have time. We have initial distance, we have initial velocity, we do not have time. We have acceleration, but we do not have time. We do not have final velocity. So our only reasonable choices are either to acquire the time and then use this equation, or use this equation. I'm just going to go ahead and use this equation because it requires less steps. So 0 squared is equal to 12 squared. I believe that's the initial velocity. Yep. 12 squared plus 2, negative 9.8 meters per second squared, times change in distance. I'll go ahead and isolate change in distance, and what we'll get is negative 144 divided by 2 times negative 9.8 is equal to change in d, or displacement. The solution then is equal to 7.34694 meters. Okay, so is this the highest that the person gets? No, that is not the highest the person gets. The highest the person gets is going to be a little bit more than that. This right here is displacement. So if we started here, right, if we were 4 meters above, then our displacement will just be this part right here. This part until we reach our very highest. So our total distance, our distance final, is going to be a distance initial plus our change in displacement, which is going to be equal to 11.34, I'm just going to round, 7 meters. That is going to be our final height. And lastly, what is her velocity when her feet hit the water? I believe we calculated this already. Yes, indeed we did. This is our solution for the last part. On to number 7. An arrow is shot from a height of 1 point. You know the drill. An angle is shot from a height of 3 meters towards a cliff height h. It is shot with a velocity of 50 meters per second at an angle of 60 degrees above the horizontal. It lands on the top edge of a cliff 4 seconds later. What is the height of the cliff in meters? Okay. So how will we answer this question? Go ahead and give it a shot and come back when you have given it a shot, or a shot or 2, or maybe 3 shots. Okay, here we go. Let's take a shot. So this is a kinematic equation, kinematic equation problem. So let's go ahead and write out our kinematic equations. Velocity final squared is equal to velocity initial squared plus 2 acceleration change in distance. Velocity final is equal to velocity initial plus acceleration times time. And lastly, the distance final is equal to distance initial plus velocity initial times time plus 1/2 acceleration times time squared. Okay, so what do we have? We have the d initial, which is going to be 3 meters. We have velocity, which is going to be 50 meters per second. We have an angle, which is equal to 60 degrees above the horizontal. And all that means is this is the horizontal, and this is above. So 60 degrees above the horizontal. It lands on top of the edge at 4 seconds later, so t is equal to 4 seconds. So let's see. Let's think about this problem for a second. I mentioned it was a kinematic equation problem. I did not mention that it was a 2D motion problem. 2D motion problems are slightly different from your regular kinematic equation problems because you're dealing with more than one dimension. There are twice as many dimensions to trick you with now if you're not careful. So this is 60 degrees. I'll put it over here, 60 degrees. This is 50. Okay, so let's see. If we're worrying about the height of the cliff, let's ask a couple hypothetical questions really quickly. This has 2 components. One that is horizontal and one that is vertical. The horizontal component is going to be, I'm going to name VIX, and then the vertical component, I'm going to call it VIY, which stands for velocity initial in the x direction and velocity initial in the y direction. A cool property about the initial velocity in the x direction is it will be constant. It will be constant. So unless there is an opposing force in the horizontal direction, the horizontal velocity will stay constant. The same cannot be said about the vertical one. The reason for this is because gravity is present. So acceleration is going to be equal to negative 9.8 meters per second squared in the y direction, at least. So let's think about this. Which one we'll use one of these to calculate the position, the height of the cliff after 4 seconds. Now which one would that be? I'll give you a hint. It won't be the x direction one because the x direction doesn't contribute anything to height. So it will only be this one. Then we can imagine it like this. Here's our arrow. These arrows represent the velocities. So, as you can see from here, the horizontal part stays constant throughout the entire thing, but the vertical one changes over time. And somewhere along here, it reaches here. Now, as the last hint, I'll go ahead and say this. If you were to throw an object upwards with the same vertical velocity, it would have the same path as this one, at least in the vertical direction. So for example, if I throw this upwards, if I throw one like this and one like this, what we're going to see is this. I'll draw this in orange. I'll draw this one in red. So as you can see, regardless of the x component, they will follow the same vertical path. So even if it was thrown vertically, they would follow the same path. So with that knowledge, we're going to use only the vertical component to determine the height. In this case, we're going to use our kinematic equations and only the vertical component. So our velocity initial will be equal to velocity initial y, which is going to be equal to 50 times sine of 60 degrees. Okay, so let's go ahead and underline what we have. We have the final? No, we do not. We have the initial, we have initial velocity, we have the time, we have acceleration, we have the time. Initial acceleration time, initial acceleration displacement. No, we have final though. No, we do not have final. I lied. Yeah, we do not have final. Okay, so using this, we can either find this and plug it in here to find this, or we can use this to find this. We'll go ahead and use this right here. So the initial distance is going to be 3 meters. Plus its velocity initial, which is going to be 50 times sine of 60 degrees times t, which is 4 seconds, plus 1/2 negative 9.8 meters per second squared times time, 4 seconds squared. And this will give us our final position of 97.805 meters. And this is going to be our height of the cliff. Part B asks, what is the maximum height reached by the arrow along its trajectory? Okay, so I'm going to go back to the analogy I gave before. If you throw a ball upwards, once it reaches the top, its velocity final will be equal to 0. It cannot go any higher. It cannot go any faster, except it can. It will go faster. It will go faster downwards. So this is our maximum height at this point. At its maximum height, its velocity will be 0. Its velocity final will be 0. So all our information is the same, except our velocity final and our, we do not have t now. So I'll go ahead and delete t. Our velocity final is going to be 0 meters per second. So with that knowledge, let's go ahead and underline what we know. We have acceleration. We do not have time. Initial velocity. We have distance initial. We do not have distance final. We have initial velocity. We have acceleration. We do not have time. We have final velocity. We have final velocity, initial velocity, acceleration. We do not have displacement. So what we can do is we have two options. We can find time, and using that time, we can go ahead and plug it here to find the final position, or we can find the displacement using this one and then add this displacement to our initial position. I'll go ahead and go with the latter. So velocity final is going to be 0 squared. Our initial velocity is going to be 50 times sine 60 degrees plus 2 times negative 9.8 meters per second squared times our displacement. And solving for displacement, we get displacement is equal to 2.209 meters. Now this is not our final position, as we started from a height of 3 meters. How can the highest point our arrow reaches be lower than our initial position if we shoot upwards? Our final position will be 3 meters? Yeah, 3 meters plus 2.209, which is going to be 5.209 meters. And lastly, what is the arrow's impact speed just before hitting the cliff? Okay, for this one, we're going to be using a couple of things. Well, our final velocity, right as we hit our cliff. Let's see, what is our? Do we have our final velocity? Okay, so right before we hit our cliff, we're traveling. After some time, this is our arrow. All right, now this is our cliff. After a change of t equals 4 seconds, we're traveling with a horizontal velocity that is the same as when we first started, but a vertical velocity that is different. And in order to calculate our final velocity, we will need these two. Those two components in relation to our final velocity is going to be as such. Velocity final is going to be equal to velocity final x squared plus velocity initial x squared. Square root of both of these. That's going to be our relationship. So since our horizontal component we know already is going to be the same as over here, which is going to be, is that 60? No, 50. 50 times cosine of 60 degrees. Oh wait, did I write it twice? Interesting. No, I wrote this wrong. My apologies. I revoke my statement. This is going to be equal to VFX, velocity of x final, and velocity of y final. So how do we calculate our final y velocity? Well, we know our initial velocity, we know our acceleration, and we know the time it takes to do that. So that's just going to be this equation right here, because we have here, here, and here. So let's go ahead and solve for that. Velocity final is going to be equal to our velocity initial, v times sine of 60 degrees, plus negative 9.8 times 4 seconds. This is going to give us a final velocity of 4.101 meters per second. So we plug this in here. And then we square both of these. And we add them. And we get a final velocity of 25.334 meters per second. Question 8 asks, you and your family take a road trip on a long holiday weekend in your Benz. This is clearly a Benz. The entire family has bands. In a certain section of the trip where the road is particularly uneven, the car goes over a bump that is curved downwards with a radius of 16.5 meters. See the diagram below. The mass of the car and its passengers is 1,800 kilograms. When the car is at its highest point of the bump, its speed is exactly 6.3 meters per second. Determine the magnitude in newtons and the direction of the force exerted by the road on the car at its highest point. Okay, so right off the bat, see if you can go ahead and figure out the solution for this problem. As always, I'm going to take an attempt. So right off the bat, I can see that this is going to be a centripetal acceleration kind of question, because they give us a mass, a radius, and a velocity, and a bump. And typically you see those in these kinds of questions. So just writing down the information. This is a visualization of what's going on here. Okay, so right at the top, the car experiences some force from this bump. Now, how do we quantify that force? Well, luckily for us, the mathematicians before us came up with this fancy little, well, quite simple equation that gives the relationship of acceleration to the velocity that you take a curve at, which is going to be equal to acceleration centripetal is going to be equal to velocity squared over r, where r is the radius of the curve. In this case, r is this, and velocity is going to be equal to this. Now, the force exerted on the ground, by the ground on the car, if you imagine it, imagine you drive across this bump, right? You drive across this bump. This bump is pushing you upwards every bit of the way, a little bit more than it normally would. It would normally just apply a normal force on you, which is going to be equivalent to your force of gravity. However, because you are taking it at such a velocity, it's going to apply that force normal plus the force centripetal to to keep you going at that constant velocity. And this force is, of course, recall the definition of force, which is mass times acceleration. We take this acceleration and we multiply it by the mass of the car, and we get the force that the ground has to exert on the car. So our final formula is going to mass times velocity squared divided by r, which is going to be equal to 1800 times 6.3 squared divided by the radius, which is 16.5. This produces a final answer of 4,329.82 newtons. Now, what direction is this going to be pointed at? Well, if this at its highest point, which is at the very peak of the hill, right here, the force is going to apply it upwards, of course. What other direction would it apply it in? Would it make sense if it applied it this way? No, it wouldn't, because that's not how hills work. Hills don't have that kind of power. At least I don't think so. So the force centripetal is going to be this way. Cool. Okay, so the magnitude is going to be 4,329.82 newtons. And this direction is going to be upwards. Now lastly, if the speed at the highest point is above a certain maximum value, the car will lose contact with the road. And luckily for you, I have this funny little video to demonstrate this effect. Witness. Now, I'm not going to enjoy the fact that that person is absolutely insane. I'm going to enjoy the fact that I understand what's going on here. The force centripetal is a lot greater than the gravitational force of the car. In other words, the mass of the car plus the absolutely massive adrenal glands of this person is not enough to keep them on the ground. They are going at such a speed that the force centripetal, the force that the ground applies on them, pushes them off the ground. We're airborne now, and eventually they'll come back to the ground and stuff like that. So if the speed at the highest point is above a certain maximum value, this car will lose contact with the road. Calculate this maximum value in meters per second. So let's see. When does this happen? This happens, as I did mention earlier, when the force of gravity is less than the force centripetal. This is when this happens. So if, for example, let's calculate the force of gravity. The force of gravity in this case is going to be 17,640 newtons, which is going to be less than the mass of the vehicle times some velocity squared divided by the radius of the curve. Let's go ahead and isolate this velocity. And thus, if we isolate this velocity, we solve for the velocity that should not be exceeded if they wish to stay on the ground. The velocity that I calculated is going to be 12.716 meters per second. The velocity has to be less than this. Oh wait, that's backwards. supposed to be here. The velocity has to be, if the velocity is greater than this, then the car leaves the ground. This is our maximum value. So that is the solution of this question. All right, so the question number 9 asks, as shown in the figure below, object mass 1 equals 1.7 kilograms starts at an initial height of h1 initial equals 0.265 meters, and a speed of velocity 1 initial equals 4 meters per second, swings downwards and strikes in an elastic collision. Object of mass 2 equals 4.4 kilograms, which is initially at rest. Determine the speed of m1 in meters per second just before the collision. Now, your first question is not, how do we solve this? I know what you're asking. You're asking, where's the figure shown below? And I must admit, I was feeling a little quirky, and I put the photo on top. Yeah, because it said below. Okay. Anyways, so let's go ahead and determine the speed of m1 just before the collision. Go ahead and take an attempt. Okay, mortal. Let's see what the actual solution is going to be. So just by looking at this, we're going to be dealing with energy, because we cannot simply use kinematics on this unless we want to be here all day. I have a dance recital I have to attend, so I must calculate the final velocity of m1 rather quickly. So what we're going to do is write down a couple formulas. First, potential energy due to vertical displacement is going to be equal to mass times gravity times height, vertical displacement. Kinetic energy is going to be equal to 1/2 mass times velocity squared. Okay, cool. And another thing is, from here to here, the change in energy will be 0. So in other words, energy initial will be equal to energy final. So let's go ahead and see what we can do about m1. So let's go ahead and find out what the energy initial is. The energy initial is going to be equal to, well, it's moving at the moment, so it has some kinetic energy, plus it has some vertical displacement. And what about its final? Well, its final position is going to be right here. So it's going to be right at, I guess, a height level of 0, and no longer has any gravitational potential. So all of it is going to be converted into kinetic energy. So if we set these equal to each other, 1/2 mvi squared plus mgh is equal to 1/2 mv final squared. We can go ahead and solve for velocity final. We see that the m's are present, so we can cancel that out. And if we isolate our velocity, this is going to be equal to our velocity, which I'm going to calculate right now. The velocity final is going to be equal to 4.604 meters per second. So determine the velocity, magnitude in meters per second of each ball just after the collision. Oh, question 10, you're not supposed to be here yet. Wait your turn. Okay, so let's see. Go ahead and take a gander at this question. See if you can make a good attempt. Okay, so right here we're going to be dealing with collisions. So we're going to have to recall a couple things. One, momentum. We're going to be dealing with momentum. Momentum is equal to mass times velocity. Momentum is a vector, of course, and typically the change in momentum in a system, given that no external force is applied, is going to be equal to 0. Now, if we're dealing with elastic collisions, we have two properties we have to recall. One, change in momentum is equal to 0. And two, see if we can recall this one, change in kinetic energy is also going to be equal to 0. Now, what about an inelastic equation? Inelastic collision. What is the difference between these two? I'll give you a hint. The change in momentum is still 0. The change in kinetic energy in this case is not going to be equal to 0. In an inelastic collision, the kinetic energy is not conserved. In an elastic collision, kinetic energy is conserved. Now, what you can do with that information is you can derive this little formula that I'm going to put right here. V1 initial plus V2 initial is equal to, oh wait, that's wrong. V1 initial plus V1 final is equal to V2 initial plus V2 final. Okay. Now, if you're dealing with a system with more than one object, you're not going to be able to use this equation, probably. Perhaps. I'm not sure. I haven't tried that yet. But only use this if you are dealing with two objects and it's an elastic collision. I should not see this in inelastic collisions, or else you'll get an inelastic grade. What does that mean? I don't know. Okay, so let's go. Determine the velocity of each ball just after the collision. Let's go ahead and set up our momentum equation. Remember, change in momentum is 0, so our initial momentum is going to be equal to m1 v1 plus m2, well, m1 v1i plus m2 v2i, which is equal to m1 v1f plus m2 v2f. Of course, v2i, the initial velocity of mass 1, of mass 2 is going to be 0, so we can go ahead and get rid of that. Cool beans. So now we have a problem because we have two unknowns. We have this one and this one. What can we use to solve for this? Well, we just need another equation. Where could the other equation be? It's going to be this one. If you couldn't see the big arrow I was drawing, we're going to be using this equation down there. So, how we're going to use this? We are going to substitute for one of these values and put it in terms of the other. So let's go ahead and use this. Let me isolate V2f because we're going to replace V2f over here. V2f is then going to be equal to V1i plus V1f minus V2 minus V2i. So we're going to go ahead and substitute that in over here. And what we get is that m1 v1i is equal to m1 v1f plus m2, wait for it, we put this here in place of v2, and what we get is v1i plus v1f minus v2i. Of course, we know v2i is equal to 0, so we really don't need that here. So we can go ahead and get rid of that. And we're left with the final equation, m1 v1i is equal to m1 v1f plus m2 v1i plus m2 v1f. And now we can solve for v1f. m1 v1i minus m2 v1i is equal to m1 v1f plus m2 v2f. Let's go ahead and isolate V2F. What we're going to get is M1 plus M2 V1F is equal to M1 V1I minus M2 V1I. Divide both sides by M1 plus M2. And we're just left with V1F. And after plugging in values, you will get a value of 4.604 meters per second, negative style. Negative 4.604 meters per second. So you might be asking, is this right? I have no idea. Honestly, I might have made a mistake here, but the process is all the same. Even if I have made a mistake during this review, the process is truly what matters. I apologize if I do not get the correct answer, but at minimum, I give you a process to go off of. So what this is saying is after this ball hits this ball goes back going this way at a velocity of negative 4.604 meters per second. That is peculiar. It is indeed peculiar because I got the wrong answer. The answer I should have gotten was negative 2.038 meters per second. Okay, so let's determine velocity to final, which is equal to up here, velocity 1 initial plus velocity 1 final. Velocity 1 initial is 4.604 minus 2.038 plus, is that plus or is that minus? Minus initial, which is 0. So the difference between that, 4.604, is just going to be equal to 2.5662 meters per second. So now that we have the velocities, we can go ahead and proceed with the last question. Okay, determine the heights to which each ball swings after the collision, ignoring air resistance. Well, I won't calculate this one because this video is getting kind of long, but this is how you would do it. The energy kinetic present in the system will then turn into energy potential, which looks a lot like this. 1/2 mass velocity squared is equal to 1 mgh. And then from here, you can go ahead and isolate h for each velocity for each ball. All right, this is the last question. It is a bit weird, heads up, but let's go ahead and let's get it. A rope is wrapped around the rim of a large uniform solid disc. Boom, boom, rope of mass 155 kilograms and a radius of 2.6 meters. The horizontal disc is made to rotate by pulling on the rope with a constant force of 195 newtons. If the disc starts from rest, what is the angular speed in revolutions per second at the end of 1.65 seconds? So initial is going to be equal to 0. And I believe that's, mass is equal to 155 kg. I believe that's all the information we have access to. So let's see. What can we do from here? Okay. Go ahead and see if you can give it a try. Alright, if you're lost, it's okay. It took me a little while to do this as well. We didn't go over this. I don't believe so. Well, we might have. It might be in the homework. But if you don't know how to approach this is how you would do it. So essentially, imagine this. You have a block, right? You're applying a force on this, and you apply this force for 3 seconds, right? Let's say this force is equal to 10 newtons, and the mass of the block is equal to, actually, let's make the force of the block to 19.6, no, 10 newtons. And we make the mass of the block 5 kilograms. What would its final velocity be if its initial velocity is equal to 0 meters per second? Well, how you would do this is, first you divide the force by mass, and you'll get acceleration. Remember the formula: mass times acceleration. Just divide both sides by mass, and you'll isolate acceleration. So from here, 10 newtons divided by 5 kilograms, that's going to be equal to 2 meters per second squared. And if we're applying it for 3 seconds, we use this formula: velocity final is equal to velocity initial plus acceleration times time. Our initial is equal to 0 plus 2 times our time, which is going to be equal to 3 seconds. Our velocity final is going to be equal to 6 meters per second. The same applies for this. Now, I don't believe I went over this in my review, but you can do this. You can do what I'm about to show you to most of the equations that you can go through. So, where there's a linear equation, there is also an analogous angular equation. So, if we're dealing with velocity, it is analogous to angular velocity. Acceleration, angular acceleration. Displacement, angular displacement. Actually, let me just do distance. Distance, beta. Displacement, change in theta. And the same applies for, say, torque. Torque is, this is on the wrong side. The angular equivalent is going to be torque. Torque is just angular force. You can think of it that way. For mass, we have moments of inertia. So, for example, if you're dealing with this, kinetic energy, right, is equal to 1/2 mass times velocity squared. To convert this into rotational energy, we can use the formula 1/2. What is mass? Mass is moment of inertia. What is velocity? It is omega. Omega squared. And this is true. This is indeed true. So if we use that knowledge, we can go ahead and deduce a formula for this as well. Torque is analogous to force. So if we divide force by mass, which in this case we'll divide torque by moment of inertia, we should get acceleration, or in this case, angular acceleration. So what is our torque? Our torque is going to be, let's go ahead and denote torque. Torque is going to be equal to force perpendicular times radius. So right here, we have a distance and a force that is perpendicular right there. So we have our torque, which is going to be 195 newtons times our radius, 2.6 meters. And we acquire a torque of 509.6 newtons. Oh, no. Newton meters. So if we divide this by our moment of inertia, we should get angular acceleration. Now, what is our moment of inertia in this case? Well, if we're dealing with a large uniform disk, we are likely looking at the moment of inertia of a solid cylinder, which is going to be 1/2 mr squared, where m is the mass of the object and r is the radius of the object. So if we go ahead and substitute that in, what we get is 1/2 mass of the object, 155 kilograms, radius, which is 2.6 squared. And we can acquire angular acceleration, which is equal to 0.9727 radians per second squared. And from here, to acquire the angular speed at the end of 1.65 seconds, we just use these conversions. We take this formula, velocity final is equal to velocity initial plus acceleration times time. Angular velocity final is equal to angular velocity initial plus angular acceleration times time. Go ahead and copy this, paste it down here. And from there we can get 0 plus 0.9727 times our time. Our time is 1.65 seconds. And we get an angular velocity final of 1.605 radians per second. And there you go. There is our answer. I hope you didn't fall for my trap there, because this is not our answer. We are looking for it in revolutions per second. So we have our final velocity, but it's not in revolutions per second. Recall to see if you can remember. Recall the conversion between radians per second and revolutions per second. Okay, so this is how it goes. We have 1.605 radians per second, and for every 2 pi radians, there's 1 revolution. How do I know this? Well, revolution is a complete rotation, just like that. A radian is a strange unit where between here and here is equal to pi. That's going to be pi radians. So a complete revolution is going to be equal to 2 pi radians. So our final answer is going to be 0.2554 revolutions per second. All right, y'all. Thank you. Thank you for watching. Thank you for staying with me this entire semester. I'm proud of you guys. You guys hung in there. You guys have taken a quite challenging course in a considerably condensed period of time. I'll be honest, when I took this back in high school, I had an entire 2 semesters to learn it, and even then it was difficult. So do not think this accomplishment is small. For you to understand this kind of concept in such a short amount of time is nothing short of remarkable. If you should thank anybody, thank your brain. Make sure you allow your brain to rest. If you are staying up at 2 a.m. doom scrolling, stop doing that. Stay up until 1 a.m. Give your brain an extra 1 hour of sleep tonight, okay? I'll see you guys when I see you guys. Good luck on your finals, yo.